Now we're going to take the four concepts we've just reviewed, system, environment, work, and energy, and relate them in terms of conservation principles. These are the most powerful concepts in physics. They allow us to solve problems without worrying too much about what goes on in the middle. We just have to figure out where we started, take a snapshot of the system initially, and then, after various forces have acted and things have occurred, we take another snapshot at the end. By comparing these two snapshots, we can learn a lot about what happened. Let's take a simple example. We'll take a jar of candy. Candy is shown right over here. It has 50 pieces in it. So we're going to first define the system boundary, and the environment. Just take a second and look at the picture, and then we'll pull down the answer. The system will be the candy pieces inside the jar. The jar will be the system boundary, and everything outside the jar is the system environment. If you know that you start with 50 pieces of candy here in the beginning, and that no pieces have crossed the system boundary, which means we haven't taken any out, haven't put any in, then you know there must be 50 pieces at the end. We talked earlier about not caring what happened in the middle of the process. In the middle, maybe the pieces could have been arranged like this, they could have been like this, but you still have 50 pieces. If this fact is true, if you have 50 pieces of candy in the beginning and in the end, we say that the number of pieces of candy is conserved. We always get the same amount of candy regardless of how they're arranged, whether they're in this necklace shape or this kind of rectangle here, as long as we take into account whether any have crossed the system boundary. In this case, we're assuming none have crossed the system boundary, so the number 50 is conserved. Now let's expand this candy jar example to all of nature. Energy. Energy is a conserved property of nature. It is not created or destroyed, so in any system where nothing crosses a system boundary that we have arbitrarily set up, we will always have the same amount of energy. This is called a closed system. The only way you can change the energy of such a system is to open it up to the environment, and you do that by adding energy to the system or taking it away. So if we're not taking away or adding anything, energy is conserved. We can do very useful calculations based on this. And the great part about energy is, unlike force and using Newton's laws, energy is a scalar. It can be positive or negative. It's still a scalar. We don't have to worry about vectors. Time for an equation to take the words we spoke and putting into mathematical formalism. We will define the energy that we start off with. In the previous example, that was how many pieces of candy in the jar. We're going to call that E0. This is your initial energy. I guess O stands for original. You could also use I there for initial. Both are used. The final energy we'll define as EF. If no energy is added or taken away from the system, we have the law of the conservation of energy. All the words we took up here we summarize in just E0 equals EF. It's a great thing about math and physics. Now it turns out there are only three ways to change the energy of a system. One is with heat, thermal energy, which won't be dealt with in this course. The other is with work, performing either positive work on the system or negative. What do you think the third one is? The third way to change the energy is probably a formula you've seen somewhere in your past. Right here, from Albert Einstein, E equals mc squared. That formula shows how mass can be converted to energy, and also energy can be converted to mass. So really, instead of conservation of energy and conservation of mass, the real law is conservation of mass energy. Now, you don't see that at the normal everyday working life. You don't see that playing baseball or riding a bicycle. But in nuclear reactions, where it's either a nuclear explosion or nuclear reactors, you have mass turning into energy. Down at the quantum level, and this is where things are unbelievably tiny, like electrons, photons for light waves, You have particles can pop in and out of existence. In other words, you have nothing, then all of a sudden particles pop out. They combine, they release energy, and as long as they do it in such a short time, and there's something called the Heisenberg uncertainty principle that governs that, then you're okay. But we're going to talk about classical physics here, not quantum, so we won't consider those cases. We'll expand the conservation of energy equation now to include the possibility of energy coming across the system boundary. And the way we're going to do that is by work. If the energy goes into the system, that's positive work. If it leaves the system, it's negative work. So our equation now becomes initial energy plus work equals final energy. And work can be either negative or positive. So here we go. If positive work is done on a system, then the energy of the system increases. Negative work done on a system, then the energy of the system decreases. The other thing this equation shows you, since you're adding things together, is they have to have the same units. So the unit of work is joules, just like the unit of energy. This slide shows the great value of conservation of energy. We can certainly solve motion problems by using Newton's laws and free body diagrams. However, if we have a non-constant force, if the force doesn't stay the same, or if we have objects moving in multiple dimensions, the calculations can get a bit complex. So we try and use the conservation of energy wherever possible, because in this part, you don't care about the forces, you don't care how the objects are moving, you just care where you started and where you finished. The original and final stage, just like we talked about earlier with the jars of candy. This, along with the fact that energy is scalar, makes the solutions much easier to get to.